since the internet doesn't want to let me on. All right. Okay. So last time we left off, we had just talked about solvent effects on these reactions. And so when you have polar aprotic solvents, these are going to tend to favor the SN2 and E2 reactions. Polar aprotic solvents look like this right here. And so what you'll see here is that you'll have these anions. They're going to only be weakly solvated, and so they're only weakly stabilized. Okay? And so you don't have as much stabilization of that anion. Now, this is really important in this case because your anions are your attacking species, right? So it'd be like having a bunch of bodyguards that are around your attacker, right? You're a little less likely to get attacked. Okay? Okay. Does it mean it can attack? No. It just means it's less likely to attack, right? Okay, so this one is weakly solvated, right? And that's the polar aprotic solvents. Okay, what does polar aprotic mean, by the way? Polar has and does not have the ability to hydrogen bond. Aprotic, not protic. Yeah. But yes, polar aprotic, poles on it, so it can do positive, negative charges. This negative ion can still be in solution, which is important because it still actually has to get there to attack, right? But it does not hydrogen bond, so it is not stabilizing this anion so strongly that it can't get out of solution. Okay? Still needs to be able to attack. If we use a polar protic solvent, on the other hand, this one will be able to hydrogen bond because it has a proton, right? Okay? And so this can do a hydrogen bond donation. Okay? It's a hydrogen bond donor. And so it will cluster around your anion. It will make a hydrated shell around it. And that's actually how anions dissolve in these. That's going to be so strong that it's not going to allow it to attack as much as it would have before. Okay? Does this mean it's impossible to attack? No, it can still attack. It's just not as high energy, right? You've lowered the energy of your reactant. And so now your activation energy barrier is going to be higher. Okay? Remember, when we're talking about SN2 and E2 reactions, you need your attacker to be a good attacker, don't you? Because that's a defining feature of that reaction. Attacker attacks. You have your concentration of your reactant, your attacker, in your rate law, right? Now, for an SN1 and E1 reactions, it doesn't matter how good your attacker is, right? Because your concentration, your attacker just does not matter. So if you have a less effective attacker, it's not an issue. You can still form your carbocation. That's going to still go basically the same rate. Okay? Not any significant difference. Okay, so let's go ahead and look at this with different rates in various different solvents for our SN2 reaction here. And so if we use a solvent which is methanol here, this is going to be a polar protic solvent. And you can see our SN2 reaction is about a 1 for our relative rate. We look at water here, and this is going to be about 7 for our relative rate. We get up here, this is DMSO, so it's a polar aprotic solvent. And this one's actually quite a nice polar aprotic solvent. Anybody know DMSO, by the way? Yeah, anybody that is familiar with like medical or dental oil or anything like that knows DMSO very well because it's the solvent they usually use to pass stuff through your skin. Okay? So if they want to put something in you without actually injecting it, this is basically how it's done. Right, most common way. And so that's your polar aprotic solvent. It is going to be a 1,300 for the relative reaction rate here. So see how vastly higher this is, right? Okay. And then again, here we have other aprotic solvents. DMF right here. These are fairly common solvents. This is a cyanide, right, by the way, methyl cyanide. And you can see these reaction rates get incredibly high. Okay. The reason these are so high, by the way, is because this is an incredibly powerful nucleophile. And so these reactions can go very, very, very fast. An interesting side note to this is actually not a very stable product. So you can actually do a bunch of stuff with this product, in case you're ever curious. All right, now this one's the SN1 reaction. And so what we're seeing here is that when we're in the protic, polar protic solvents, our relative SN1 reaction rates are going to be much, much higher. Okay? Whereas when we're in the aprotic solvents, we're going to have a lower reaction rate. And again, this is because we're going to stabilize that anion when it leaves, right? So remember, when we're talking about this reaction here, we need this, the iodide, to be as stable as it possibly can be, right? Because our high energy product, which is the carbocation and the anion, the better that they separate and stay separated, the better we can go over that energy barrier, isn't it? Okay? And so it's actually kind of interesting that this solvent choice actually works on both parts of this. It makes the carbocation more stable to generate. It makes this more difficult to do. Okay? So it's a very, very impactful choice, in fact. And there's tremendous amount of time that's spent just figuring out the perfect blends of solvents to optimize reaction rates and get the best yields possible, so that you can get a 90% yield versus a 92% yield, because that 2% could literally be the difference between billions of dollars in all the industries that would be applicable to. So you guys would be really shocked about how many man hours, how many hours are spent on this stuff. The SN2 reaction rates in ethanol for this reaction right here, if we use this for our nucleophile here, this would be our relative SN2 reaction rate. And so these would be for ethanol, which is going to be a polar protic solvent. And so you can actually notice that depending on your reactant, it can actually change your reaction rates. Now, these are very high numbers, by the way, because this is the baseline number here, which is actually really low. Okay. Okay. So one of the things that's very interesting about this is you may have noticed like bromide was not usually this amazing nucleophile before. This all of a sudden has become like way better of a nucleophile, right? And so has like the sulfide. Okay. And the interesting thing about this is that it has to do with the fact of how well these things bind to our protic solvents in these cases. So you can actually make this kind of really crazy modulation, where if you're really careful about it, you can actually cause different nucleophiles that you may have competing in reactions to have different reaction rates by adding a bit of protic solvent. Okay, so this is sort of like secondary effects that you may be able to think about, but right now we need to concentrate on this. But know that when you add a solvent, it can actually change your nucleophility of your different nucleophiles. Okay, which is a better nucleophile. Okay, so this right here is going to be the solvation effects on your energy barrier of your reaction. And so what you're seeing here is the solvation effect is going to work by causing this reactant to lower energy for these SN2 reactions. The lower that energy is for that reactant, then the larger the barrier we have to overcome. Okay? And so the better it solvates something, the lower that energy is going to be, right? And so, for example, you see here, chloride is much better solvated than the bromide. And so we get this huge shift in behavior where this bromide just becomes incredibly good versus the chloride, right? Huge difference in that relative reaction rates. Okay, so let's talk about heat, because that's where every conversation always ends up at. I'm realistic about chemistry. All right, so increasing the temperature of reaction tends to promote elimination more than substitution. So you can actually start favoring your elimination products if you allow the heat to go up. If you lower the heat, you can start favoring the SN2 products instead. Your eliminations are going to be favored when you increase heat. Now, this right here again is the same conditions. Notice that the only difference is 45 degrees Celsius versus 100, right? And so at 45 degrees Celsius, you see that the substitution product would be 47%. The elimination is 53%. Okay? The elimination is still favored in this, but you get a lot more substitution product. When we increase the heat to 100 degrees Celsius, though, we go down to 29% for the substitution and 71% for the elimination instead. And so you'd have actually quite little of the product being produced. Okay? All right. So notice that, remember when I was like, you need to keep this within this range for the temperatures? That's why that stuff's important. Okay? You can actually start favoring the production of a different product if you allow it to start going very hot or very cool. Okay? All right, so this is going to be temperature and entropy that are going to affect this. So remember that when we make our substitution product, we're making two products here because one of them stays on it, right? When we make the elimination product, on the other hand, we end up with three products because none of them stay on there. We just eliminate everything, right? Make a double bond. And so which one has greater entropy again? More products, right? Less products, less entropy. Okay? And so this is actually a reaction that is going to be favored by this entropy. Or another way of thinking about this is thermodynamically favored in terms of entropy. Okay? What do we know about entropy, by the way? Yeah, it's a measure of randomness, or another way of saying is the number of microstates it can be in, right? Number of states it can be in. But another thing we remember about entropy is, have you guys ever seen this formula? Yeah. What do you notice about this term? It relies on temperature. So the greater the entropy, the more effect the entropy has on driving the reaction, the higher the temperature. Okay, that's why ice melts, by the way, and like gases are formed from liquids when you have higher temperatures. This term is increasing as you have higher temperature. In case you're wondering. So you have more entropy for a liquid than you have a solid. Yeah. Yes, you have to add heat to the solid. Mm-hmm. Yeah, it's a well, it is a, you can consider a reaction. Yeah. It'd be a phase change reaction. Mm-hmm. Okay. Some of the strategies for success for predicting these. Step 1, determine whether an SN2 or SN1, E2 or E1 competition is even feasible. If you don't have the conditions for one or more of those things, then you can just get rid of it, right? You don't have to consider it. And so you can save yourself mental bandwidth. So for example, the leaving group should be at least as stable as fluoride. That's the cutoff. Fluoride is sort of the least stable of the anions that you're ever going to actually see. Unsuitable ones would be things like HO minus, RO minus, H2N minus, H minus, and R minus. Notice those are those super basic things, right? That were like pKa's in the 50s and 40s and stuff, right? So very, very high energy forms. Very, very high energy products. Leaving groups should be bonded to an sp3 hybridized carbon. A recognizable attacking species should be present to act as a nucleophile or base. It needs to be something that could actually act as a nucleophile or base. If you don't have a pair of electrons to the bond, it's not going to happen, right? If you add a metal, that's just not going to act as a nucleophile or base if it's just the metal, right? And so you need to have something that you can recognize as a nucleophile or base. to some degree. Okay. Now, step 2 is going to be rule out reactions that are going to be unfeasible. The biggest one for this one that's going to be the one that pops out, at least when you practice a bit, is the tertiary carbons. It's a tertiary carbon. You don't consider the SN2. You can't have it. It's a primary or methyl carbon. You don't have to consider the SN1 or E1 unless the resulting carbocation is resonance stabilized. Because remember, resonance stabilization bumps that stability of the carbocation up to the next step. Okay? Okay. So, like methyl carbons, very unlikely to produce a carbocation with a methyl, right? Primary also very unlikely. Okay? Secondary, tertiary, much more likely. Or resonance stabilized. Rule out E2 and E1 if there's no beta hydrogens. If you don't have an adjacent hydrogens at all, you can't do it. And so this can happen on things like rings oftentimes, or you have very, very branched structures, and you literally have nothing. Okay? Now, I do want to add one caveat here, okay? Which is that if you form your carbocation, you can cause methyl and hydride shifts, right? But typically those are going to be energetically disfavored forming them. Like your intermediate is already energetically disfavored. It's going to be a fairly slow reaction to form those, okay? But it is a caveat that you may have to consider in some very edge cases, okay? Okay. Now, get anything on this? The solvent can also help you rule out some of this. So, for example, SN1 and E1 reactions, you can look at your solvent to help you rule these out. So remember that an aprotic solvent is going to favor your SN2s and E2s, right? Okay. All right, so let's go to the next. Determine which of the remaining reactions are going to be favored by your attacking species. So up to now, we've looked at the conditions. We've looked at can it even leave? Have a leaving group that's a good enough leaving group? And so now we need to look at the attacker. This is the last part. Now, there's a lot of problems that will never reach this step. A lot of problems, you'll do these first 2 steps, and you'll be done. Okay? So if you've already eliminated it down to one option, then you're done, right? You don't have to consider the next part at all. Okay? I know all of you are kind of looking at me, why is he talking about this? But it's like a major problem people run into on tests. They've actually eliminated it down to one option, and then they sit there and they eliminate the last option off. And go, what's going on? So if you got down to one option, you're done. You can try to double check, but don't let you talk yourself out of your answer. Which is very possible, right? All right. Now, step 3, determine which of the remaining reactions are going to be favored by your attacking species. SN2 is going to be favored by a strong nucleophile. SN1 is going to be favored by a weak nucleophile. You can also have a low concentration of a strong nucleophile, right? Which is typically called dilute, DIL, right? E2 is going to be favored by a strong base. E1 is going to be favored by a weak base or by low concentration of a strong base. Now, the hardest one for all of you that you're going to run into and have difficulties with is the SN2 versus E2. Okay? Because what makes a strong nucleophile versus a strong base, it can be a little bit on the subtle side, right? But remember that this is step 3, okay? The vast, vast majority of problems are going to be determined by steps 1 and 2, okay? And step 3 is just going to be, do I have an E1 or an E2, okay? Very few problems you are still going to have an E2 and SN2 that are still options, or an E1 and SN1 that are still options on the table. Okay? It's actually a pretty rare one. So remember to do these in order. If you don't do them in order and you try to skip steps, you can run into cases where you're going to confuse yourself. Okay? And you're going to end up talking yourself out of answers. Right? Okay, so the next parts. Now we're on the tiebreakers. At this point, I'm going to be honest, like 90% of the answers you should have already gotten. Okay? If you're getting down to a 4 and 5 of tiebreakers, you're going to end up being, we're talking much more minutia. Okay? We're looking at much smaller effects than the previous parts. These previous parts were really big ones that you can't even do some of these things, right? Yeah. Okay. So step 4, we're going to apply the appropriate tiebreaker to the remaining reactions. Tiebreakers for an SN1-E1 reaction are going to be determining whether heat is added to the reaction. E1 is going to be favored if heat is added. SN1 is favored because in the absence of heat, and that's because of this right here. Okay. And so again, remember, we're looking at minutia now. More than 90% of answers you would have already come up with. If you haven't come up with an answer before you get to a tiebreaker, I'd actually recommend going back through this process and double checking that I didn't make a mistake. Okay? But you will run into, I'll probably give you a question sometime this year that you may have to get down to a tiebreaker. Okay? The likelihood is about 50-50 if I'm going to give you a question like that. Okay? It just is, did I happen to click on the one of, like there's I have 3, I think, out of 7 that have that. So that would be these more difficult ones. All right, so the tiebreaker for SN2 and E2 reactions. You're going to determine whether attacking species acts better as a base than a nucleophile. This is very subtle, okay? And so the attacking species acts better as a base and thus favors E2 over the SN2 if it is bulky. Okay? If it's bulky, it's not going to be able to attack very well. Otherwise, your SN2 and E2 can remain favored. In fact, you do have reactions where these will be competing reactions. You will get both products, and so you would have 2 to 3 products depending on what you're looking at. Okay? And so, yeah, it is possible that you will have multiple. It's unlikely I would give you a problem like that. Okay. Okay. Does anybody have any questions there? At least this semester. Next semester, fair game. Okay. I know. All right, so let's apply steps 2 through 4 on this reaction here. Okay, we have this reaction. We have the chloride. That's going to be our leaving group, right? We have the bromide here. This is going to be our attacker. And we're in DMSO. Okay. So first off, what sort of solvent are we? Aprotic polar solvent. Got it. Yeah. Okay. Second off, is that a valid leaving group? Yeah, that's a valid leaving group. Okay. So we have a valid leaving group. Do we have hydrogens we could take off here? Yeah, we do. Yeah. There are only 2 bonds to this carbon, 1 bond to that carbon, right? And so this has 3 hydrogens on it. This one has to have 2 hydrogens on it, right? So we have hydrogens we could take off to do the E reactions. We have the leaving group that can leave. And this is a nucleophile. It can also act as a base under some conditions. So we're valid up to this point. Okay? Okay, so we have an aprotic solvent. Now, aprotic solvent means we're going to favor what sort of reactions here? SN2 and E2. You got it. Yeah. This is not going to greatly stabilize the others, right? And so the SN2 and E2s are going to be the ones that are favored by this aprotic solvent here. Okay? And that's your step 2 now. Okay, step 3, we circle and keep the reactions that are favored by our attacking species. And so is bromide going to be a better base or a better nucleophile? Well, bromide's one of the conjugate bases of a strong acid, isn't it? Okay, so it's a miserable base. It's a terrible base, right? Now, what it is, though, is it's very large, and it has very, very deformable orbitals that can reach out and get into places, right? And so this is a better nucleophile. And so this nucleophile bromide here, this does favor your SN2 reactions here. E2 is disfavored here. Now, do we actually have to do anything for the next parts? Yeah. In fact, once you have a choice, like, it doesn't hurt to go, hey, can I verify that choice and be more confident of it? But don't talk yourself out of it. If you're going to try to go, I don't think this is right, go through the whole process again, okay? And re-ask yourself the questions, okay? Don't try to talk yourself out on step 4. Step 4 is just not as important as steps 3, 2, or 1. They're very much in order of importance, okay? Okay. It'd be like talking yourself out of picking up a $20 bill because meteorite may land there. Okay. Yes, meteorite might land there, but probably not a realistic concern, right? The lower priority. Okay. Okay. So your mechanism for an SN2 conversion of an alkyl chloride to an alkyl bromide is this one right here. And so we have the SN2, the bromide attacks on the backside attack, the chloride leaves here, and that gives us the opposite. See, this used to be the wedge, right? Now it's the dash. Okay. Anybody have any questions? Testing. Very good. Okay, so again, this is another example of predicting an outcome here. So the first thing we always have to do is, hey, is our can we do this reaction? Is it even possible? Okay. So that first step, bromide, is that a leaving group that can leave? Yeah. Sure. Do we have a nucleophile somewhere in this? Yeah, this can act as a nucleophile or base, can it? So we have something that can act as a nucleophile or base. Do we have hydrogens on the next one over? Okay, how about this one, and this one? They would have hydrogens, wouldn't they? And so we could do an E, we could do an S. We're still, all our options are available in step 1. Okay? We're still good to go, and we can actually do these reactions in the first place, which is possible we can't, right? I mean, very possible. This could be all methyls here, right? And that none of those are leaving groups, right? Okay? We can have those situations. There are reactions, there are some things that just do not do any of these reactions. Okay? We'll talk about other reactions we can do with those later on. But for now, these reactions. Now, we're going to cross out reactants that can be ruled out in here. So we look here, and what do we see about that? Carbon right there. Is it primary, secondary, tertiary? Yeah, tertiary carbon, right? Tertiary carbons can't be attacked easily, can they? They're very difficult to attack. Okay? And so that automatically says that SN2 is just not possible, is it? Okay? We just can't get in to attack it. Now we can still get into here to attack the hydrogen. So the E2 is still possible. Okay? That doesn't limit our E2. The other thing we have to consider now is that we are going to go on to the next step. And we're going to have to figure out, well, which one do we favor now with our actual attacker? Okay? And so right here we see, well, this one right here is going to be, well, is that a strong, in this case, base? We don't have to actually consider strong nucleophile. It's not a strong base, not a strong nucleophile, it's not strong anything, is it? Yeah. This is just methanol. And you all kind of knew this because you used methanol, you got it all over your hands, and you didn't get reacted, did you? So, good thing. All right. By the way, that's actually a literally a very valid test for that. If you got a strong nucleophile base on your hands, guess what? You're getting reacted with, aren't you? These reactions happen to you too. So, all right. So we would favor right now our SN1 and E1 reactions. So we now have to go to our step 4. We weren't able to eliminate everything else. And so step 4, what does that delta here mean? It means heat. Yeah. Delta in these contexts where it's the reaction conditions is referring to like a delta H, a delta temperature, right? So we're going to increase the heat on this. Okay. So if we're heating this, what does heat favor again? Elimination. Yeah. So we'll keep the elimination there. Okay. And we don't need anything else. We're done. Yeah. There's no other conditions here we have to worry about. Okay. Is everybody starting to get comfortable with our process? Okay. Really do practice these though, because you need to have that process in order. And the best way to sort of gain familiarity is go flip cards first, so you have the steps down, and then practice it, which I gave you lots of problems to practice with. You're welcome. Yeah, your face. Yeah. Fair enough. All right. And so this is the E1 reaction, right? We have the heterolysis. The bromide comes off. We're left with the carbocation. It's highly stabilized. But in this case right here, we actually are going to take off this hydrogen here with our base. And that's going to give us our double bond. And so then we're going to go to the major product, which is this one right here. Okay. By the way, this one doesn't really have a, like the other way is the same thing. So the major product is just the only product in this case, because it's the same every direction you go. Okay. This would actually be the SN1 for that reaction, in case you're curious. And so this right here is going to not be a major product. But remember, we're only doing this on step 4 that we choose between them, right? And what do we remember about these steps? Like, this is just it can happen or can't happen, right? This one also is a huge one that you're going to basically see none of the other, right? This one, again, is a pretty big one, but you could start maybe seeing a 1-2% sort of stuff. And then this one, we're talking about minutia here, right? Little tiny advantages, okay? And so we could see, I mean, if there was nothing favoring any, we might get something close to a 50-50. If we favor one, we're going to get like a 20%, 80% sort of stuff. We're not going to get all of one, okay? And so that's our major product. Down here, we have our minor product, which is going to be the SN1. Again, it has the exact same first step. We then attack our carbocation, and we'll have the deprotonation step right here. And that gives us this right here, it's the methoxy product. An interesting little factoid about these is if you had carbocation rearrangements that could happen, you'd actually start having more products you could make. Okay, depending on stabilities. But 2 for now. All right. So this is another example. I want all of you to start trying this out. So go through the process. Now, don't forget to actually go through these steps on your flip cards and each of the things that qualifies on those steps. Because one of the things I usually don't point out here, because we don't have a lot of examples, and I just don't do them, is that it needs to be an sp3 hybridization, right? On that step 1. So that carbon for your leaving group has to be sp3 hybridized. It's just not something I like. I don't get to work through examples much if I stop. Yeah. And memorization is usually pretty easy. At least, 5 things. Okay, folks. Everybody got their answer in their head? Yeah, you got to commit to one. And SN1, SN2, E1, E2, and then the fifth secret answer, super special answer, doesn't happen. Okay, everybody committed? Okay, so step 1, what's our leaving group? Yes, you got it. The OTS, perfect. The tosylate. Yep. Very, very good leaving group, right? Are we attached to an sp3 carbon? Yep, we're attached to an sp3 hybridized carbon. You got it. Do we have something that can act as a anion, an attacking species here? Do we have some sort of attacking species? We do. We do. What sort of attacking species? That's the solvent. But this is the attacking species here, right? Okay. And so this right here, this sodium's going to come off. We'll be left with an oxide, right? Okay. And that is, in fact, tert butoxide. Okay. All right. So do we get to eliminate anything so far? No eliminations. We're still ready to go for everything, aren't we? Okay. Okay. And so for step 2, what are we going to start eliminating out? Look at the solvent. It's a good one. Yeah. And basic also will be the next part of that. Yeah. So you're both right. This both happens at that step. So the fact that we have an aprotic solvent, polar aprotic solvent, tells us which steps are going to be favored here. SN2 and E2. You got it. And so we had a base, right? It was a bulky base. And so which one are we going to tend to favor here? Yeah, we're going to tend to favor a little bit E2. Now, this this is a strong nucleophile, by the way. Okay? And it's a strong base. So it's actually both. This is a bulky one, though. Now, the bulkiness is actually going to factor into the next step. Okay? But you were correct. It is a strong base. You got it. So at this step, we would still have in the running for our step 2 here, we would still have all of those in the running, right? And then we would cross off the E1 and SN1s. The SN2 and E2 are still going to be left behind, okay? Okay. Now, you are absolutely correct for step 3. When we were looking at step 3, I'm just trying to make sure it's divided up among steps so you all can follow this a little bit better. That when we got down to step 3, we would have considered the attacking species. This is going to be an alkoxide. And so it is a good base. It is also a good nucleophile. Okay? But in this case right here, it's going to be a bulky one, right? Now, step 3 is not where you would normally actually truly consider the bulkiness of it. This would actually typically be considered step 4. Okay? So step 4 is going to be the tiebreaker. Now, it being the bulky species does favor one of these, and that was E2. Perfect. Perfect. Sorry, I had to go a little bit further. I just wanted to make sure you guys had structure. Okay. And so we get the E2. Very good. Okay. And so this is actually your mechanism for your E2. You're going to attack this hydrogen here. Notice that the anti has to be anti to the leaving group if you're doing an E2, because your electrons actually have to flow through that orbital system. Okay? And so it needs to be this conformation here. This one is actually not anti, and so you can't attack this one over here, which is actually kind of an interesting thing you may not have thought about. This mechanism. Okay. So we attack this one over here. It puts the electrons in our double bond, and our tosylate leaves. This is going to be our major product right there. Very good. Okay, so let's draw a complete mechanism and predict the products for the reaction shown here. In this reaction, we have this reactant right here. It's going to be dissolved in methanol. So without anything to structure yourselves around, you got to predict this now. I'm going to give you another minute or two, and then I'll start moving along, okay? Try to work through as much of that as you can. To your choices. When it's 51, I'll move to the, and we'll start doing it together. Let's go. They got your commitments, at least to the first parts. Okay. Okay, so the step one, right? Do we have a leaving group? Is that leaving group on an sp3 hybridized carbon? Do we have a recognizable attacking species? Yeah. Yep, we're still good to go, aren't we? Okay. Step two, what reactions can we rule out in terms of substrate, solvent, leaving group ability, absence of beta hydrogens being the ones next one over, right? Okay. And so again, the substrate right here, this is a primary, isn't it? Okay, and so we don't have to worry about tertiary blocking things out. This is going to lead us to a pretty unstable carbocation typically. However, we do have a mitigating condition here, and that is this right here. That can do resonance structures, can't it? It's a benzene ring, okay? So if we make a carbocation here, it's going to be resonance stabilized. So that is still a possibility. Okay. All right. The substrate, again, benzylic, that's what that's called, in case you were forgetting the naming for benzenes. And so we do, however, have one really, really important factor here. How many bonds does that carbon right there have? 4. And so how many hydrogens? 0. And so are there any beta hydrogens? So we finally found an example of that. That's the sort of thing you'd see for a 0 beta hydrogen. And so you can't do eliminations at all, can you? Yeah, there just is no hydrogens to eliminate off. E2 and E1. Yeah, both of those are ruled out. All the eliminations are impossible. Just can't do any. Pretty crazy. We finally got that one. It takes a while to get them all. So we still have the SN1 and SN2 reactions that are possible. And so now we have to go on to step 3. We have an attacking species, which is going to be methanol again. It's an uncharged, weak nucleophile. And so that's going to favor which of those, SN1 or SN2? Yeah, that would favor an SN1. You got it. Okay. So SN1 is going to be your winner here. Now, if we hadn't figured out that we don't have an E that's possible here, we'd actually have we'd still have to consider E1, right? And so see how important it is to do these in order and make sure you eliminate those before you get to things. Because if you ignore that, you're going to be sitting here like What's SN1, E1? What am I doing? Where do I go? Okay. We don't have to do a tiebreaker because we already got one. Okay, leaving group leaves. We're left with the carbocation, resonance stabilized by this ring. And then we attack it with our weak nucleophile here. This is going to be give you a proton on that oxygen. And so we actually do have to do a proton transfer step. Note that we didn't put any wedge or dash here because of the carbocation here. We'll end up with a planar structure. And this is going to mean we get a mixture of the attack from the top, attack from the bottom, right? Okay, front or backside attacks. And so we'll get a mixture of the different products. As anybody's wondering, this is a valid way of saying that in organic chemistry, where you just do a single bond, no wedge or dash, and then you put mixture of R and S. The other way to do that is you put a wiggly. So what you would do that's the other symbology for a mixture. Okay? You see that more in advanced textbooks. This you see more in like intro textbooks. Okay? Because that one, imagine if you saw that when you first started. Oh, yeah. I can really mess you guys up and confuse you, right? All right. Now, let's talk about regioselectivity in elimination reactions and the different alkene stabilities. Specifically, we're going to be looking at Zaitsev's rule. Okay, and so right here we have a species that's going to undergo an elimination reaction. And what we see is we have a 68% chance of producing this one right here. And this one over here, we have a 16% chance. Do you notice any differences between these? This one's more substituted, isn't it? Okay. And so a substrate can possess 2 or more distinct hydrogen atoms that can be removed in elimination reaction. This can lead to 2 or more possible alkene products. And this elimination reaction is going to exhibit what we call regioselectivity, that it selectively does it in a certain region. Okay. And so in this case, what we're going to see is it's always going to favor the more highly substituted carbons, okay, which is this one over here. The one that is less substituted is disfavored. Okay, why is that? Well, we look over here, we have the same reactant for both, so that's the same. And then we come over to our products, and what we see is the more substituted alkene is lower in energy. And you may recognize that from the previous chapter, actually. We had talked about that same sort of trend, right? And so the less substituted alkene is actually higher energy. And what that means is that if you have a higher energy product, your barrier is higher energy as well, isn't it? Not a lot, but a little. And, a little bit of a rate difference can make a lot of difference in terms of winning a race, right? Okay. And so, again, we get most of our product being the lower energy one. Some of our product ends up the higher energy one because it is not that big of a difference. Okay, so let's talk about the increasing stability of your double bonds. It's the more substituted, the more stable it is. So tetrasubstitute is the most stable, trisubstitute is the next most stable, and then we have the disubstituted. If the disubstitute is all in one carbon, that's going to be your most stable of the disubstitute. If they are across from each other, the trans, or E, this is going to be the next most stable. And if they're cis, this is the least stable of your disubstitute. And then we have the monosubstitute, only one substitution. Okay. Now, why would it be less stable like this than this? Steric repulsion. Remember when we have bulky groups near each other, they repel, don't they? Yeah. I definitely was giving you a chance to think about it and refresh. And saw a lot of you go, oh yeah, steric repulsion. So steric repulsion, same reason as we had been talking about in, I don't remember, remember how many chapters ago that was now, but it's been a while. So cis isomer is going to be less stable because of that steric repulsion. The CH3s are going to repel each other. And then the trans minimizes that repulsion, just like we were talking about anti-conformations. Okay, so this is, again, another example of Zaitsev's rule here. And so Zaitsev's rule is the major elimination product is the one produced by deprotonating the carbon atom initially attached to the fewest hydrogen atoms. Okay, some of these rules are kind of weirdly phrased, but notice that's essentially saying the more substituted one is favored. Okay. And so again, this is just Zaitsev's rule. That's what we had just talked about in terms of the stabilities. Okay. So the hydrogen comes off of which side again? The one with the fewest hydrogens, right? The not hydrogen things. The more substituted one. Okay. Now that I've taught you a rule, let's violate the rule. Okay? We're rebels in this class. So, there are exceptions, of course, to any rule of chemistry or any rule of science. Rules in chemistry and science are not laws, right? And even laws should be questioned. Okay? And so, an E2 reaction that can exhibit anti-Zaitsev regiochemistry with a strong bulky base is this one right here. And so if we have a strong bulky base, what are we going to have happen when we try to attack a region with more substitution? Well, it's going to have more repulsion, isn't it? And so if you use a strong bulky base, you can actually flip Zaitsev's rule. Okay? And this is, again, because it's going to cause more repulsion when it's trying to come in to attack that hydrogen, the more substituted you are, right? And so this is actually the anti-Zaitsev product. It's produced by bulky bases. And so this one is it right here. Here we're going to have the empty pi or anti-bonding molecular orbital and see how that's effectively isolated here. If we have this with another substituent on it, what we can see here is it's no longer fully isolated, is it? And so this is now going to be overlapping with hyperconjugation with this hydrogen bond here. Okay, it's going to help stabilize that anti-bonding by allowing electrons to flow into it. Okay. And so it's going to, again, going to be a, this is how, excuse me, I didn't really set this up, did I? Okay. Other thing, we're getting on to something new. Wow, I'm really could have used my water, but I forgot. Okay. Now, again, this is your anti-bonding orbitals for a double bond. This is those electron orbitals that you're going to actually have to flow electrons into. So when we have these anti-bonding molecular orbitals right here, what you'll notice is the more substituted you are, the more you're going to have orbitals that will overlap that have electrons in them. These are going to actually cause the electron energies to go down through hyperconjugation. You may remember hyperconjugation in terms of carbocations. Okay? And so this is that same concept, but for the anti-bonding orbitals. Okay? So when we start looking at these alkene stabilities, what you'll notice here is the alkane stabilities go again on substituted to monosubstituted to disubstituted to trisubstituted to tetrasubstituted. And this is why, as you add more orbitals that can overlap, you're actually going to stabilize these anti-bonding orbitals here. Okay? And so you're going to help stabilize all of these molecular orbitals that are the sigma anti-bonding molecular orbitals, what they're actually going to do. Okay. And so your entire structure actually helps stabilize itself. Now, the chemical reaction between two separate species is going to be an intermolecular reaction. And so again, inter, be like interstate, right? Internet. between molecules. Reactions typically require two separate functional groups. This is kind of a grab baby of things I'm going to be going through that I'm trying to finish off the chapter. And so typically they're going to require two separate functional groups. These functional groups need to be on separate molecules usually. However, instead, they can be on part of the same molecule. That molecule is going to act as a backbone, and it's going to be said to be an intramolecular reaction, i.e. intra like intranet, right? And so intra within, okay? Intravenous within, right? Okay. And so you've already seen some examples of this before, but you may not have realized it. Now, one of the important factors is this typically has to be something that's at least 5 or 6 members long, so it can wrap into a stable chain. Okay? So 6 is going to be your most stable, most likely for you to see this happen, so that it can wrap around back to itself. Okay? If you have 3 members here, you're not going to be able to reach. So right here, we have a leaving group on one side of the molecule. We have an attacker on the other side that can act as a nucleophile. And so we can actually get attack within the molecule. And that's an intramolecular SN2 reaction. It's still an SN2. You still have 2 parts, an attacker and a leaving group, right? But it's all in the same molecule. And so you'd have a second order with your own molecule. So kind of an interesting, fun one. This is the intermolecular reaction. This reaction would also happen alongside it because it can also run into another molecule, right? In which case we would get the intermolecular interaction, the intermolecular reaction, and the intramolecular reaction. You can tell I just was talking about intermolecular interactions. Another glass. Okay. So why is this so important? Well, this is actually happening to your sugars all the time. Okay? So your sugars typically are in the form of rings. 99-point-something% of your sugar is actually in the ring form in your blood. And so this is being done all the time with your acetyl functional groups, and these are forming your complex carbohydrates. This right here is an acetyl carbon, in case you're wondering. Okay? And this is what makes it acetyl. It has that other oxygen right here. Okay? And see, it's also joined another one. And so this would be a large sugar structure of some sort. Okay? Now, the natures of these linkages is actually seen in a simple acetyl formed from glucose. This is the generic acetyl. You may hear hemiacetyl. If it's a hemiacetyl, what would that be? You got it. So you're missing one of these. Okay. All right. So this is your glycosides. These are your structures. I know we like to put them like this because they're very easy to identify, but straight chain carbohydrates are incredibly unusual. Okay. The vast majority in physiological conditions are in fact rings like this. And so we had actually somewhat practiced this. And so what you're actually seeing is this is forming that hemiacetyl here. And those glycosides are going to be formed as a mixture of diastomers. And it's going to depend on which side this is. We're going to replace this with a methoxy instead so we can see this easier. Okay. So instead of the OH, we're going to put a methoxy here just so we can see it a little easier. Okay. But what it's going to be is, see this carbon here? Okay, if you're on the same side as that carbon, you're going to be a beta. If you're on the opposite side, you're going to be an alpha. Okay? And so this one's a beta, this one's an alpha. All right. And so that actually gives you a diastomers of these 2 D-glycosides right here, if you do this reaction. Okay, so this is the oxygen right here that we're looking at. This is the acetyl carbon here. Okay. Okay, if this is on the opposite side to this carbon here, which is the 6th carbon, then this is going to be an alpha. So this is an alpha D glycoside. Or it would be, if it was just glucose, it would be an alpha D glucose. This was an OH. This right here, see how it's on the same side of the ring? That's a beta. I usually find it easier because beta looks like it's lifting itself up. Alpha looks like it's down. So, okay, so this right here is actually the mechanism for glycosides formation of a sugar. You'll notice that it's a continuous equilibrium. It happens all the time in your body, continuously, if you're looking at just regular sugars. But if you're looking at glycoside reaction, it's going to, again, be a continuous equilibrium reaction. And so this is going to be this oxygen getting attacked, acidifying. Once we do the proton transfer, this is a really good leaving group. It can leave, forming our carbocation. Once we form the carbocation, it's a resonance stabilized carbocation, which is what you're seeing here. We can attack from either side, and that's going to cause that to form the two different diisomers, right? We'll have front side, back side attacks. Okay? And so we'll end up with a mixture of these that is both of the different diisomers, which is what you're seeing right here. Okay? This one being the alpha, this one being the beta. And then we deprotonate that, and that gives us our final product here. Okay. So let's talk about glycosides in nature instead, right? So we get a very, very similar thing that happens with glycosides in nature, but in terms of nature, we typically join up different sugars, okay? And so this right here is cellulose. It's going to be a continuous chain where your monomers are your glucoses, and they're going to be beta 1,4 glycosidic linkages. So notice the beta right here, right? Same side as that carbon, okay? This is the first carbon on that one. This one over here is the fourth carbon. And again, that's just going to be your acetyl being formed right there. Okay. And so that would give you cellulose. This right here is the two different forms of starch, which are amylose and amylopectin. Okay. And so that's going to be the water-soluble, water-insoluble starches that you may recognize from diets. These are going to have slightly different linkages that are possible. They're both have the same main chain, but when you start talking about amylopectin, they're going to have more side chains coming up. Okay, so this is your main chain. It's going to have an alpha 1,4 glycosidic linkage. Notice again, opposite sides of that carbon, right? And over here, we again still have the alpha 1,4 glycosidic linkage on our main chain, but then we have our branches come off as alpha 1,6 glycosidic linkages. And that's that 6th one right there. This one's the 1 alpha. Okay. And so these are very highly branched structures. We actually store a very similar compound in us. This is going to end up being an even more branched structure. I'm not going to go super far into that. You can go to biochemistry. Now, one of the reasons cellulose is so hard to break down is because you actually need an enzyme that actually works on a beta 1,4 glycosidic linkage, which is a very different looking bond, very different looking structure. I'll note that these form very, very nice kind of straight strands, whereas these form these sort of loose spin helices. Okay? And so that's why cellulose is a structural component, right? All right. So these are the glycoside hydrolysis, in case you're wondering. So in the presence of water and an acid, it can also be done in a basic environment, but acid is going to be the more likely environment because you'll do it in your stomach, okay? And in your saliva. That's why your fingers get sticky. So this is glycosidic hydrolysis. We're going to have the beta D glycoside, and we're going to add water under acidic conditions. Notice under acidic conditions, this deprotonates, and we can go ahead and have that become a much better leaving group, right? And then we can attack that with the water and put the OH on. It's going to give us two products, which is the alpha D-glucose and the beta D-glucose. Okay? And that's the sort of reaction you would see in your stomach, actually. Because notice that's stomach environment. Now, it is an equilibrium. It will go back and forth continuously. So, anybody have any questions there? No. Okay. That's some of the things you can do with the reactions we've just talked about. We'll start on the next chapter next time, so I only have a minute.